Welcome to the next video in the series on condensed matter theory. In this video I want to talk about Bloch's theorem. And Bloch's theorem is something that we will use in further lectures and videos where we will derive properties of materials in a periodic potential, or where we approximate the material by electrons moving in a periodic potential. Welcome to the next video in the series on condensed matter theory. In this video I want to talk about Bloch's theorem. And Bloch's theorem is very useful when we want to talk about properties of materials or electrons moving in periodic potentials. And actually we will use this theorem, for example, in the next video where we will derive properties about the conductance or the Hall effect. And just based on Bloch's theorem, we can make very general statements of the properties of those materials. And Bloch's theorem tells you the properties of eigenstates in periodic potentials. And it states that all eigenstates can be written as a function of a plane wave with the wave vector that is the crystal momentum times a function that is periodic in the crystal lattices, such that u tau of r plus r is equal to u tau of r. So u is a periodic function and that is a plane wave with a crystal momentum. All eigenstates are of this form. Any wave function that is of this form we will call a Bloch wave. And this is a very useful formula that we will use in the next videos or next lectures to derive material properties. In this video I would like to show you two different proofs of this theorem. One is based on the property that only states with the same crystal momentum interact with each other, and the second proof is based on symmetry arguments. So let's start with proof number one. And we go to two proofs because they basically show you the ideas behind Bloch's theorem, and Bloch's theorem is so general and important that it's good to grasp this in detail. So we've seen before that we can write our wave function as a sum over all reciprocal lattice vectors, some complex number times a plane wave with the wave vector that is the lattice vector, where psi k plus q is equal to square root 1 over v e to the I k plus q dot r. If we put that in, we find the sum over all lattice vectors of g alpha q tau square root 1 over v e to the I k plus q dot r. We can take the e to the I k r outside, is e to the I k dot r, and then we have the sum over all reciprocal lattice vectors alpha q tau square root 1 over v e to the I q dot r. Now this is e to the I k dot r, and this function we will call u tau of r. In order to prove Bloch's theorem, we now have to show that u tau of r is periodic in the lattice. And we have u tau of R is equal to a sum over all reciprocal lattice vectors alpha q tau, some complex number, and then a plane wave with the wave vector q. So we can have a look at u tau r plus capital R, so shifted by a real space lattice vector, which is a sum over all reciprocal space lattice vectors q tau, a complex number, square root 1 over v e to the I q dot r plus capital R is e to the I q r times e to the I q capital R, and e to the I q capital R is 1 by the definition of the reciprocal lattice, and therefore what we have here is just u of r. So we indeed find that our eigenstates can be written as a plane wave with the wave vector of the crystal lattice, the crystal moment, times a periodic function in R. So that concludes the proof of Bloch's theorem. Now let's have a look at the second proof, which is based on symmetry arguments. And for that, we're going to define our translation operator that takes a point R in space and brings it to R plus capital R. So we shift our lattice by a lattice vector. And our Hamiltonian is invariant under this symmetry operation. So this is an operator that should commute with the Hamiltonian. So we find that T R to R plus capital R commutes with the Hamiltonian. So the energy of a system is the same after you've translated it by a lattice vector. Now let psi k of t be a non-degenerate eigenstate. Such that h psi k tau of R is e k tau psi k tau of R. Well, if it's an eigenstate of the Hamiltonian, it's also an eigenstate of the transition operator. So we know that T R goes to R plus capital R of our wave function is the eigenvalue, some complex number, times the wave function. Now a translation shouldn't change the norm of the wave function. You don't get more particles when you make a translation. So we know that not only is this some complex number, we also know that the norm of that number has to be 1, as the wave function doesn't change in normalization. Now when I make a translation by a lattice vector R, and then I make a translation by a lattice vector R prime, or I can make at once a translation by the lattice vector R plus R prime, I should get to the same state. So we know that T R goes to R plus capital R, T R goes to R plus capital R prime, should be equal to T R goes to R plus capital R plus capital R prime. Or in other words, Ck of r times Ck of r prime is equal to Ck of r plus r prime. Well, the function as a function of r that has this property is the exponent. So we know that Ck dot r is equal to e to the power r. The norm has to be 1, so it is IR, and I can put here an arbitrary phase. And up to now we have not really defined what k is in our derivation. So we can say that k is the phase that you pick up when you make a translation. And we are free to define what k is. At this point we only said here that we have an eigenstate with two indexes, k and tau. So we can always label states that have the same crystal momentum or the same k. They pick up the same phase when you make a translation by using tau. And there is no meaning given yet to this quantum number, which is what we do here. And we say when we make a translation, then the crystal momentum tells you what the phase change of that wave function is. So the result that we find is that if we make a translation and do this of our wave function, then what we have is the wave function translated, evaluated at a different position, and that is e to the I k dot r times the original wave function. This is an equivalent statement to the original form in which we wrote down Bloch's theorem, and you will find Bloch's theorem in both variants. If you put in psi here, then you immediately find that u is a periodic function and that these two statements are equivalent. So also here we have proven Bloch's theorem. So besides the properties that we can derive from materials just based on Bloch's theorem, such like things like conductivity or the Hall effect, having positive and negative effective charges for the conductors, we will in later lectures also use that we can relate this periodic function to the atomic functions that we have on our atoms when we do tight binding theory, and then we can really show the equivalence between starting with the atomic eigenstates and putting them in a lattice, or starting from a plane wave basis and putting on a periodic potential as a perturbation on there. Which makes Bloch's theorem extremely practical and extremely useful for the description of material properties. Very well, in the next lecture we will start with calculating the electric conductance in a solid in a periodic potential. For now, thank you for your attention, stay healthy.